In this video, we'll be discussing Spearman's correlation coefficient. First of all, there are other types of correlation other than Pearson's correlation. Recall that Pearson's correlation looks at the linear relationship between two continuous variables, x and y. These different correlations can have different purposes and establish slightly different relationships between the variables. That is, they may or may not look at linearity, monotonicity, and other different types of relationships that we can assess. There are two primary versions of correlations that are worth mentioning. The first one is Spearman's rho. And recall that the rho character is a Greek P-looking character. The other is Kendall's tau. And a tau just looks like a T. In this course, we'll just discuss Spearman's rho as the non-parametric alternative to the Pearson correlation. Spearman's correlation computes the monotonic relationship between two variables. Monotonicity simply means that as one variable increases, the other variable increases. This is very similar to what we saw with a linear comparison, but this doesn't have to increase in a line. It may increase in a curve, a quadratic curve, it may increase in a logistic curve, but as long as when one variable increases by any amount, the other variable increases by any amount, this is a monotonic relationship. Again, monotonic focuses on the idea of increasing as opposed to increasing at a certain rate, which is what the linear increase is in Pearson's correlation. Note that because of this, we are no longer dealing with linear relationships. So this is a method that can determine a relationship even if that relationship isn't necessarily linear, as long as the relationship is a monotonic increase. The calculation for Spearman's correlation is actually surprisingly easy and is based on the Pearson correlation calculation. First, we take the values of x, the first variable, and rank them from smallest to largest. That is, for the smallest number, we put 1. For the next smallest number, we put 2. And so on. One interesting thing to note here is we take an average for ties. So let's say that the first three numbers were tied, that we would normally give the ranks 1, 2, and 3 to. In that case, we take the average of the ranks, so we average 1, 2, and 3, and we would give each of those three values a rank of 2 before moving on to the fourth value, which would have a rank of 4 unless it also was tied. When you're doing this, though, don't reorder the values. That is, don't order them from least to greatest. We want to keep the order that the x values originally came in and keep the order that the y values originally came in. This is also important when dealing with the Pearson correlation, and something that we didn't fully discuss. But whenever we're looking at any type of correlation, the order in which the x's and y's come in is important because we're looking at the relationship between the x's and y's. That is, if we change the order in which the x's and y's come in, where we change the order of x without also changing the order of y in the exact same way, we're no longer looking at the relationship between one value from the x and one value from the y and whatever would connect those two values. Now we're repairing a different set of values which may or may not have the same meaning or relationship. After we've done taking the values of x and ranking them from smallest to largest, we do the same for y. After we have these ranks instead of the regular numbers, we simply calculate the Pearson's correlation on the ranks instead of the original numbers. This is why it's important not to change the order in which the numbers come in. Let's go through an example quickly. First, let's grab our data set from above. Here we have the data set that we've used previously with X and Y. Our goal now is to rank X and Y in increasing order from the smallest to largest. I'll do this independently for X and Y. That is, I'll do it for all of the X values and then restart and do it again for all of the Y values. The lowest number in the X vector is the number 4. Now remember, we have ties, and in the case of ties, we average. So the first two values would be 4 and 4. That would be rank 1 and rank 2. Instead of assigning rank 1 and rank 2, I take the average of 1 and 2. The average of rank 1 and 2 is just adding them together and then dividing by how many numbers I added. So this is just our regular old average that we would use. Using this equation, we find this average to be 1.5, so I'm going to enter the rank of 1.5 for both of these values. The next lowest number is 5, and again, there is a tie for the number 5. So after assigning ranks 1 and ranks 2, or in this case the average of them, 1.5 and 1.5, the next two ranks left are 3 and 4. So in these cases, again, I'm dealing with ties. I'm going to start at what I would normally have started at if I didn't have any ties. So first two values, that's ranks 1 and 2, I would start at 3 and 4. So in this case, I'm going to average 3 and 4. It's going to give me a rank of 3.5 for both of these 5 values. So now I've got ranks 1 and 2. I've got ranks 3 and 4. My last rank is 5, and that's going to be for the number 6. The Y vector is going to be much easier because there are no ties. I simply start at the lowest number, 2, and enter 1, the first rank. For the next lowest number, 3, it's the second lowest number. The third number is 6. The fourth number is 9. And the fifth number is 11, again going from least to greatest. 1 is the smallest, N, or 5, is the largest. Now, when I'm ready to calculate my Spearman's coefficient correlation, I simply take the Pearson's correlation of these ranked values. So I would literally type in as my data 1.5, 1.5, 3.55, 3.5 in the exact order that they appear in. So 3.55, 1.5, 1.5, 3.5. And I would take the Spearman's correlation of these ranks and these ranks and correlate them with each other, and that's my Spearman's correlation. After running this, you'll get rho, and I'm going to use rho sub S to indicate that this is a Spearman's correlation, not the theoretical value of the Pearson's correlation, which was also called rho. And my correlation is 0.791. Now, if you remember, this is slightly different from our previous correlation that we had using the Pearson's correlation for the same data set. Real quick, let's talk about a couple of images that illustrate the differences between Spearman's and Pearson's correlation. Let's draw a graphic that indicates a monotonically increasing, but not linearly increasing, pattern. Something like this would be a good indication. Note that there's not a line that really connects all these dots, so the pattern does deviate from linearity. However, as x goes up by 1, each y goes up, even if it's just by a little bit. As x goes up by another one, the y goes up again, even if it's just by a little bit, and so on and so on. What this means is that this graph indicates a perfect monotonic relationship. This would be monotonically positive, again, because it's starting at the bottom left and going up to the top right. So we would have our rho sub S be 1. This is a perfect Spearman's rho. In comparison, calculating a Pearson's coefficient for this Depending on exactly what equation was used to make this, Pearson's correlation may be something like 0.8, or a little bit lower or a little bit higher depending. So this is a great indication of how these are different, where we have a Spearman's, perfect Spearman's, but we have a Pearson's correlation that isn't perfect. Now there are similarities too, and there are patterns that we can see where both of these statistics are going to indicate something different. For instance, a pattern that we saw earlier, or something similar to what we saw earlier, is this quadratic relationship. Now note that as x goes up at the beginning, y goes down, but then in the last half of the graph, as x goes up, y goes up. This indicates that there isn't a monotonic pattern. Monotonic says that every time x increases, y increases, even if it's only a little bit. Every time that x goes up a little bit, y goes up, even if it's only a little bit. So the fact that sometimes in this graph, x increases while y decreases, and sometimes in this graph, x increases while y increases, means that there's a difference. That is, the directions of the movement of y as x increase conflict with each other. Thus, our Spearman's rho, in this case, would be a perfect 0. For every increase in y when x increases, there's an equal decrease in y when x increases. Similarly, our Pearson's correlation is also going to be 0 because this doesn't cluster around a line. This is a good demonstration visually of the similarities and differences between Pearson's and Spearman's correlations, and a good illustration of when you may choose to use one versus the other, depending on which type of relationship you're interested in. Are you interested in a relationship that's monotonically increasing? If so, you may choose to use Spearman's correlation over Pearson's correlation. There are also some other reasons you may choose to use Spearman's correlation over Pearson's correlation that we'll discuss just now. Spearman's correlation has some really interesting and useful properties, some of which are going to seem very similar from the Pearson's correlation, and others which will be starkly different. First of all, the range of the Spearman's rho is going to be very identical, frankly, to what we saw in Pearson's correlation, with the range being from -1 to 1 inclusive, and -1 and +1 indicating perfect monotonic relationships. This is also scale invariant, and if you look up in your previous notes as to what scale invariant means, it was a it was a property of the scale where if we change the scale of x and y, the statistic doesn't change. We can also swap x and y similarly with no change in Spearman's rho. Now we get to some differences. So these are all very similar. These first three are exactly the same as properties of Pearson's correlation coefficient. However, where Pearson's correlation measured the degree of the linear relationship, Spearman's measures the degree of the monotonic relationship, which we illustrated just a moment ago. One final consideration, or a couple of final considerations, but one really important one, is that this requires ordinal variables, not necessarily continuous variables. So if you remember your scale of measurement, you have nominal, ordinal, nominal, ordinal, and then continuous, which would be interval and ratio. This only requires ordinal data, that is, data that have ranks. This opens up an entirely new set of data to analysis than what Pearson's correlation can handle, which is a very flexible and beneficial property of Spearman's correlation. Incidentally, it's this property that makes Spearman's correlation not as sensitive to outliers. The fact that we're using ranks allows us to use ordinal or ranked data, and it also means that outliers don't skew the data as heavily. Finally, this statistic is part of a family of statistics called non-parametric. And this non-parametric alternative simply means that instead of assigning a distribution to Spearman's rho, we actually use the ranks themselves to come up with the distribution, allowing us to not make assumptions such as normality. This has been a brief presentation on Spearman's rho and how it compares to the Pearson's correlation, including some of the benefits and detriments of choosing Spearman's rho over Pearson's correlation.